shape with this material. So a Riemann sum is simply a collection of approximations for blank under a curve. Area, that's right. So, whoops, there we go. So area under a curve. In the video, I talk about these scary looking symbols. This right here should not look too scary. Isn't that the thing we've been doing for the last couple of days? Riemann sum. And in the video, I talk about why this over here is essentially the same thing. It's the difference of basically saying we want the number of rectangles to go towards infinity, or we want the width of the widest rectangle to go to 0. Either way you look at it, you're making the number of rectangles go to infinity, and you're making the width of the rectangles head towards 0. In either case, depending on the book that you look at, they usually have both of these definitions. In either case, this is the definition of what we call the definite integral. So, a couple days ago, I said something along the lines of, if somebody was peeking over your shoulder, maybe like somebody in Algebra 2, and they saw you doing like ddx of this and derivative and all that stuff, and they said, hey, I've heard of this derivative thing. What is a derivative? What would you say? If they said, what is a derivative? I've heard about it. Explain it to me. What would you say? Say again? Slope of the tangent line? Instantaneous rate of change. You could also say slope at a point, kind of goes along with the idea of slope of the tangent line. So, if in the future somebody saw you drawing the tall skinny s thing, like these, and they said, hey, what is this tall skinny s and all the other stuff there? And you're like, oh yeah, that's an integral. And they're like, well, what's an integral? What you would say is it's an infinite summation of skinny little rectangles. It's an infinite summation of super skinny rectangles. I usually just say it's an infinite summation. Really is what it comes down to. That's really what a definite integral is. You're just adding up a bunch of really skinny little rectangles areas. It's going to give you some number that represents the area of all those summed up. But that's what a definite integral is. So let's see here. Down below it says, you can see this down below the yellow highlighted section. It says an indefinite integral, which is what we've been doing for a while. An indefinite integral is a blank of functions. What did you put in there? See it? Say again? Family. It's a family of functions, that's right. And the family of functions really just depends on what the plus c is. So it's a family of functions, could be a specific function depending on what the plus c is. But a definite integral is not a family of functions. It's a number. Okay? And the reason why it's a number is because the definite integral is connected with the concept of area, and area is often represented simply just by a number. Okay, so then in your video, you have the opportunity to kind of practice with this one right here a little bit. We talked about this one before. I want to do a couple of different things with this. I want to review and make sure that this all makes sense. If we're going to set up a Riemann sum for this, we would say limit as n goes to infinity of sigma from I equals 1 to n. And let's see here. The interval width is how far? 4. So my base length is 4 over n. And then the height is going to be 5 input, right? So I'm going to put 5 times input. And then what is the lowest possible input? Negative 3. And then we're going to add to that 4 over n I. Okay, so I hope you watched the video. Maybe you remember this. Didn't we talk about this one? Yes? No? Yeah? Okay. I hope that you're in a good place where you can set this up, and you'll get a couple more opportunities to practice this here in just a second. But what I thought we would do, I think I've got room. I might have to run this onto the board. We'll just have to see how it goes. I thought we'd maybe evaluate this all the way through. We'll do this once, maybe twice. I just want to show you that this actually works, and I thought we would use this particular function because I think it'll be pretty easy to confirm that the answer we get is right. Because when you look at those two blue shapes, what are the shape of those two blue shapes? And we all know how to find the area of a triangle pretty easily, so we should be able to confirm that this is actually true when all is said and done. So here we go. The first thing I think I would do here is I'm going to get the 5 and the 4 over n out, because the sigma really only applies to the I. So what I think I'll do is this. I'll write limit as n goes to infinity. If I pull the 5 and the 4 over n factors out, it's really a 20 over n. So I'll put 20 over n sigma from I equals 1 to n of negative 3 plus 4 over n I. And here's where we're going to apply some sigma operations, right? So it's sigma of negative 3 plus sigma of 4 over n times I. So if we wanted to, we could look at it like this. We'd go limit as n goes to infinity of 20 over n, and then it's sigma of negative 3 plus sigma of 4 over n I. Bless you. And this would be the point in the game where the formulas that are in your notes, the ones that you don't have to memorize, here's where they're going to come into play. So if you need to peek back and check these out, it should be just on a previous page or two. Looks like, yeah, one or two pages there. So look at the upper left one, the one that says sigma from I equals 1 to n of c. C just being some constant. Do you see how that applies to the first one? So what is the sigma from I equals 1 to n of c? Cn. Okay, so let's see if I can make this work out here. So it'd be limit as n goes to infinity of 20 over n times the quantity of negative 3n plus, I am going to try to, does it make sense, when I look at this, I can show you an additional step here if you want. Does it make sense that in that second one, the sigma only applies to the I? You're sigmaing, you're adding from I equals 1 to n. I can actually get the 4 over n out of that one. Here, let me just show you a little step of explanation here. So what I could do with this is I could rewrite it as sigma, or sorry, I could rewrite it as 4 over n sigma from I equals 1 to n of just I. Because the sigma applies from I, right, equals 1 to n. So the 4 over n is just more or less a constant multiple as far as the sigma is concerned. So when you look at it from that perspective, wouldn't it be fair to say that we're just doing sigma of I? So looking at your little formula sheet, what is the sigma of I? So yeah, there's an old mathematician, well, they're old now, but when they supposedly came up with this, supposedly very young, the name of this mathematician was Gauss, quickly found out a way to sum up the first n integers. So it really is a pretty amazing formula. So if I said to you guys, hey, what is the sum of the first 1,000 integers? So 1 plus 2 plus 3 plus ... all the way up to 1,000, right? You could take one of two tracks, right? You could sit there and go 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, so on and so forth, right? And it would take you forever. Or you could think of it like this. Can you picture this in your mind? I can draw a picture if you want. If you're numbering 1 to 1,000, if you start at the ends, 1 is over here in my left hand, 1,000 is over here. 1 plus 1,000 is 1,001. Now move in. 2 and 999 adds up to be 1,001. 3 and 998 adds up to be 1,001. 4 and 997, 1,001. So you think about that for a second. Well, so if you start moving your way in, won't those pairs always add up to be 1,001? Well, how many pairs would there be? 500 of them. So if you just went 500 times 1,001, done. Right? So that's what Gauss supposedly came up with as a 6th grader, I think, like a 10-year-old or something like that. Pretty phenomenal, right? Pretty phenomenal thought process to see that pattern. Okay, so I'm going to continue on to the board here. I know I'm out of room, but check this out. if I were to then say limit as n goes to infinity, I think what I'll do is I'll distribute that 20 over n back in there. I got it out just to make these steps pretty simple, but I'm going to multiply it back in. When I multiply the 20 over n times the negative 3n, wouldn't the n's cancel? Now I just get negative 60. You guys with me? So negative 60 plus, and then when I multiply the 20 over n in there, wouldn't the n's cancel and the 20 over 2 would also cancel? Yeah. So the n's are gone. The 20 over 2 becomes a 10, so I'd say 10n plus 10. Does that make sense? N's canceled. Yeah, 10n plus 10. Question?
Would you do it to 4 over n?
Yeah.
Oh, shoot.
That's what
My bad. Here, let me go back. I know I knew I left this running for a good reason. It belongs in there. Sorry. That was just an oversight on my part. So 4 over n times n plus 1 over 2, right? Does that make sense now? Sorry. I definitely just forgot that. Okay, so the first term is still right. Let's redo that second term. So now, let's see here, the n's, the 4, so it's like 240. So I'm getting plus 40, like so. No, it's this. No, it's what?
Oh, wait, no.
Cody times 1 then, no?
You have what, Ben?
You go with 40 and n plus 1. You can just do 40 n plus 1 over n.
Yeah, we can do some simplification still. I'm just multiplying it and making sure that or trying to make sure that I transferred everything over. Yeah, so it's 80 over 2, which is 40, n squared, n still on the top. We're just doing algebra here. I know I say just, doesn't make it easy, but don't think that it's anything other than algebra. Do you see how the n and the n squared would cancel once? So then this would be gone. That'd be to the first. We end up with that right there. Is that okay? Yes? No? Do you have any questions? Okay. So limit, let's just simplify a little bit here. Negative 60 plus 40n plus 40 over n, like so. And I think now at this point we're ready to apply our limit. Limit as n goes to infinity. The limit as n goes to infinity does not apply to this at all. Does not apply to this at all. But it applies over here. And over there you could use a variety of ways to simplify and solve, or not solve, but evaluate that limit. Couldn't you use the degree trick? So the degree at the top and the bottom are both 1, so the limit as n goes to infinity should simply be the ratio of the lead coefficients. In this case, it's 40, right?
Yeah.
40 over 1. Okay, so this just ends up being negative 60 plus 40, which is negative 20, right? Hello? You with me? Question, Ben. No, say it again. What if you did what?
If you just take out the 40.
Oh, sure. Yeah, because, well, then n plus 1 over n would simplify to be a 1 when you do the limit as n goes to infinity. You get 40 times 1. Same thing. Yeah, same thing. Okay, can we talk about why this is? I feel like somewhere in here I've lost you. Some of you, somewhere in here you're just kind of like, I could never do this. Stop for a second. I will never, ever ask you to do this. Not that you can't do it. It's simply not worth our time. Can we be honest with this for a second? Beyond the setup, are you guys all okay with the setup? And when I say setup, I'm talking about, are you all okay with this line right there? That's the thing we've practiced a lot of. Now, everything that follows there, from a time perspective, I am not going to make you do this on a quiz or a test. I am simply not going to do that because it's going to take you 15 minutes on a good day to do that, isn't it? It's not worth our time on a quiz or a test. But the algebra, getting the formulas straight and all those things and me not forgetting my 4 over n notwithstanding, this is all doable stuff, right? It's all very doable stuff. There is a reason for this, and the connection is this. Is anybody looking at that and saying to themselves, how on earth, I'm going to erase all this, how on earth do we find an area and the area is negative? Think about that for a second. That's really strange. It has to do with below the x-axis. Remember what we said at the start, and we said in the video too, that a definite integral is nothing more than an infinite summation of infinitely skinny little rectangular areas, right? So, if we want to look at it from that perspective, all the way for this whole domain right there, aren't all of the y values negative? And so when we tell the integral, hey, we want you to sum up a bunch of stuff, it's just going to be adding up a bunch of negatives. And so the result should be negative. But then when we ask the definite integral to add up those, aren't all those y values positive? Yep. And so it's just going to add up a bunch of positives, so shockingly enough, it'll come up with a positive number. But when we put these two together, let's go ahead and do some rectangular areas here. This right here, this rectangle, the base length is 3, right? If you just looked at it purely as a rectangle, base length is 3, and what is the height? Is that right? 15? Okay. And then this one right here, the base length is 1, and the height is 5, right? Okay, so 1/2 times 3 times 15, what is that? So 45 times 1/2, 22.5. Okay, so 22.5 there. And up here, 2.5. Here's how we would actually end up getting back around to our answer. Because all of those y values are negative, this will actually end up integrating to be negative 22.5, right? Because a definite integral is nothing more than an infinite summation of infinitely skinny rectangles. So that would integrate to be a negative 22.5 because it's below the x-axis. This would integrate to be a positive 2.5 because it's above the x-axis. So when we finally accumulate all of this, we would say this integral equals negative 22.5 plus 2.5, which of course is negative 20. Okay. Say again?
So that's a whole lot easier.
It is. And so listen, here's where you can make a mistake in your thinking. You might be thinking, gosh, Mr. Anderson, why on earth did you show us that stuff you showed us? I am really interested in you understanding where it comes from, what it means. I do not want you, listen, the last thing I want you to say is this. My teacher is a real neat teacher and he knows a lot of stuff and he's taught me all these tricks and I have no idea where any of it comes from, but he taught me some tricks. Right? This is a really easy trick and Lainey, believe it or not, there are going to be times when the thing I just did with those rectangular areas is exactly what I want you to do. But if somebody were ever to say, how does a tall skinny S have anything to do with some triangular areas? I don't want you to be like, I don't know, but it works. It's neat. My teacher taught me a cool trick. I want you to be like, oh, okay, well, it's kind of a pain, but if you took these rectangles and you added them all up and you did the summation formula stuff, you'd actually end up with the same thing. I don't want you to be able to explain something like that. Does that make sense? But you know what? We will use rectangular areas, triangular areas, all kinds of easy things to make these easy. I just want you to know where it comes from and what it means instead of there's a trick. Make sense? I agree with you that this is easier, and so we certainly will use this at times. Let's practice this. This will be kind of our last chance to do this together before we get on towards like Thanksgiving break and all. I want you guys to take a look at these two examples here, numbers 2 and 3. And I want you to try these. These go along with the video. These go along with what we've done. Notice number 2 says set a Riemann sum expression that is equivalent to that definite integral. And number 3 gives you a Riemann sum and asks you which integral it goes with. Make sense? I will say this, that on my tests, on an AP test, I would say that in all likelihood, the way you would see yourselves assessed on this is like number 3. Okay, so I can assess the connection between Riemann sums and definite integrals without making you do that 15-minute thing that we just did. So if you guys would, try numbers 2 and 3. Based on the video, I think you have a fair shot to do this, and we'll put these together here for you in a couple of minutes. Let's decide how you did. So if you are ever asked to write a Riemann sum expression, start with the easy stuff first. And isn't the easy stuff the limit and the sigma? So we start there and we say limit as n goes to infinity of sigma from I equals 1 to n. So that's a good start. Now I'm going to put in the next easiest thing. The next easiest thing is my base, or the base length of each rectangle. What is the full interval width that we're considering? Isn't it from 3 to 8? So it's 5. So the base length of each rectangle would be 5 over n. And then as far as the height, so far we have limit sigma of base. We need to multiply the base times the height to get the rectangular area. Isn't the height simply determined by the y value of the curve? And the y value of the curve is input to the fourth minus 1. Input to the fourth minus 1. So then to get that input, we need to consider really two things. Number one, what is the lowest conceivable output for my interval? And you would say? 3. Agreed. But then we need to actually progress across the region. And so we need to add to this. And every time I add to get to the next rectangle, how much am I going to add? 5 over n. And then I need to multiply that by I, because I need to actually progress all the way across the region to get to the other end. So if you've got that right there, awesome. And now I'm looking around and I'm seeing people that are like, yep, I got it. Am I right? Trying to read faces. Lauren's trying to play poker with me, but now she's not. She's giving it away now. Anybody have any questions? That's a very confident face on Lainey there. Am I right?
Yeah.
It's great. That's exactly what we want. That's great. Okay. So then, really, to be honest with you, isn't number 3 just kind of going the other direction? It's going the other way. It's starting with a Riemann sum and going back to a definite integral. So to build this out, we're going to start easy. Oops. And starting easy to me just means there's my integral symbol. I'm going to go ahead and set up my domain. So what do you guys see as the lowest possible input? -2. It's -2, isn't it right there? That -2 tells us that's our lowest conceivable input. And then the full interval width is 9, and don't you see that in 2 places? There and there? So if we're going to go from -2 to something and the full interval width is 9, where would I stop? 7. So didn't that just eliminate those two? Those two are out. And now you look at what's left over, and the only thing that really differs is a minus sign. And so I would encourage you to look at it from this perspective. And by the way, can anybody tell me what what is equivalent to the 9 over n? In A and C, which symbol is equivalent to the 9 over n? Say it again. The dx. Whoever said that? Yeah. The dx, that's the 9 over n. So really it comes down to the height. And so the height is right here. I guess the way I would put it is this. When I look at the height, do you guys see it this way? Do you guys see basically input cubed plus 5? As opposed to the opposite of the input cubed plus 5? Can you see that in there? Like the parentheses would be the input, so input cubed plus 5. And so because of that, I would go with C. So Ben, you were right. Didn't you say C earlier? Yeah. So I agree with you on that one. Okay, so a lot of you folks, in fact, it seemed like the majority of you said, yeah, number 2 went well. How about number 3? Number 3 go okay? Thumbs up from Matt and Alex. Oh man, thumbs up everywhere now. Excellent, Eliza. Do you have any questions at all? I feel like you guys are picking this up extremely well. So Lainey, we're going to come back around to your thought of, wow, can we just do it that way? So check this out. So that's kind of what this little section is all about here. It says using areas to evaluate definite integrals. So if f is piecewise and it's made up of familiar shapes, like triangles and rectangles and squares and stuff like that, then geometric area formulas can be used to evaluate these definite integrals. And listen, this is 100% permissible in these situations. I have no problem with it at all. The AP folks don't have any problem with it at all. You can't use this when the graph is curvy. That's kind of the point. But if you've got these line segments, then you can certainly do what we are about to do. So I've got a series of questions here, all based on that graph of f of x. So maybe I'll do one of these with you, and then I'll kind of turn you loose and see what you guys can do with the rest of them. So that first one there says integral from -4 to -1 of f of x. And so in this case, we are talking about this area over there. So if you had something like this, you're like, hey, look, it's piecewise, it's linear, all these little line segments going everywhere. What I would do is this. I would say the base length of this triangle is 3, and the height is... Come on there. Yep, there we go. The height is 4. And so if the base is 3 and the height is 4, what is the area of the triangle? -6. Well, we'd say 6, right? I think I mentioned in here, we're never going to say that area is negative. We'll never say that area... Be careful though, Hannah. Be really careful. This is a finer point. You might have the right answer down there. We will never say that area is negative. So area of that triangle is definitely 6. But remember, the integral is not like a area finding machine. All the definite integral is going to do is it's going to add up all the stuff that you tell it to add up, right? So if you tell it to add up a bunch of negatives, it's going to spit out what kind of answer? Negatives. So the answer to this question is -6. If I asked you what's the area of that triangle, you would say 6, but what is the integral going to spit out? It's going to spit out -6, right? Does that make sense? Okay. So, armed with that sort of thinking, will you guys try the other 4? And it's all about geometry formulas. In this case, they're all triangles. So please give it a shot. So the second one there is the integral from 1 to 2 of this function. And so that would be this orange triangle. Did you guys notice the orange triangle has the exact same... Oh, 1 to 2. My bad. Let me
That's 0.
fill in the right one.
That's
Duh. I have kind of a fat marker here, and there we go. 1 to 2. Okay? So from 1 to 2, the dimensions are 1 by 2. So did you guys get an area of 1? Okay. Now, should the integral spit out a 1 or a -1? Why 1? It's above the x-axis. So we'd put equals 1. Now, oops. Now, if we're going to do the integral from -4 to 2, aren't I going to have to consider all of this, the whole gray area, as well as the red area? Make sense? So the dimensions here are 3 and 4. Same dimensions. So the area down here was 6. The area up here is 6. But those are just areas. As I accumulate from left to right, won't this gray area show up as a -6? And the red area would show up as a +6? So you should get -6 plus 6, which is 0. Does that make sense? Yeah? Any questions on that one? All right, I'm encouraged by that. And then the integral from -1 to 4. So -1 to 4 would be this and this. That's 6. What about that rectangle, or what about the triangle that's below? 4. So the area is 4, but below, because it's below the x-axis, it's going to show up as a -4. And so the integral would spit out a 2. Make sense? Final question. And this is the only question that actually asks you for area. It says, what is the total area between f of x and the x-axis on -1 to 4? And that's the interval that I have highlighted up there. Well, the first area we got was 6, and the second one was 4. So what's the total area? 10. Remember, area can never be negative, and so we would consider the 6 to still be a positive 6, and the 4 would be a positive 4 because we're talking about area as opposed to just doing an integral. So a key takeaway here is, do you understand the relationship between the definite integral and area? Because they're very much related, aren't they? What's the only thing that could possibly be negative? The integral, right? The definite integral could spit out negatives. If you're ever asked for area and you get a negative number, something went wrong. Yes, ma'am.
So why do we do like all the x values are always going to be positive, but then the y values can be negative? Like,
So you know what it is? It's the difference in the x's. That's a great question. So like, let's take this this blue area, for example, and let's say we just did a representative rectangle, and let's say I did it from here to here. Make sense? So what we would say there is we would say the area just for that rectangle itself, we'd say area equals base times height. Now the base is delta x, isn't it?
oh, okay.
So it would be -2, or yeah, -2 minus -3 times the height is -2. Okay, and so then you'd have essentially a positive one. So the delta x will always be positive because it's a delta x, not just an x. Good question. Anybody else? Okay, well, let's finish this up. We'll see. We might be able to finish all this up. I think we'll come very close, if not all the way. So we're going to look at some properties. These properties are all pretty much based on area. And so I think that hopefully these will make a lot of sense to you. Let's take a look at numbers 4 and 5. First one hopefully makes a lot of sense to you. The first one says if you've got the integral from a to a of f of x, you should always get
A number.
very specific number. I think I heard it. It's 0. If you try to calculate the area between two numbers and those two numbers are the same number, what's the base length? 0. It doesn't really matter what the height is. The area is going to be 0, right? So, guys, maybe not this directly, but believe it or not, you will see examples where you got to calculate the integral from 4 to 4. And you'll just want to say 0 because you know this property. Number 5, there is a deeper reason for this, and we'll get to it into 4.4. But for now, if you've got the integral from a to b, and usually a is the lower number numerically, and b is usually the higher number numerically. It doesn't have to be that way, but that's how we're accustomed to seeing it typically. But if you wanted to or needed to switch the limits for some reason, all you have to do is switch the sign on the integral. Like I said, there is a deeper reason for this. We'll get to it in 4.4. But the integral from a to b is equal to the opposite of the integral from a to b, or from b to a. So if you switch the limits, you switch the sign to accommodate that. So do you see in our example, do you see how the lower number physically is actually higher numerically? So that's not the customary way of doing this because we usually accumulate from left to right instead of right to left. So what we might say is this is equal to the opposite of the integral from 2 to 5. Notice how I switched locations for the limits. And I'm allowed to do that as long as I change the sign on the front. Okay? Just a couple more here. Please take a look at numbers, well, just for now, number 6. Number 6 looks pretty complicated, but if we look at this like area, in terms of area, I think it'll make a lot of sense. If I look at this integral right here, integral from a to b, wouldn't it be fair to say that that could be representative of this area right here? And then the integral from b to c is representative of this area from here to here. So if I take the purple area and I add it to the red area, wouldn't I get the whole area?
Yep.
So the integral from a to c equals the integral, like the little part on the left plus the little part on the right, should give you the whole thing. This can be done backwards as well. You could, instead of putting it together like we're doing, you could break it apart into pieces. Same principle though. So an example down below, if you've got the integral from 1 to 3 plus the integral from 3 to 7, we could condense these down into just a single integral from 1 to 7. Yep, so integral from 1 to 7 of f of x dx. In order to do this, the integrand, the f of x, needs to be the same function. If they're two different functions, you can't do this. But if they are the same, then you certainly can. Still doing okay? All based on area. Do you see why we put so much effort into area? Maybe these make a lot more sense based on that. Okay, and then our last two are over here, number 7 and 8. These two are actually old ones that we've talked about with indefinite integrals, and so these shouldn't feel too terribly new. If you've got an integral from a to b of k f of x, with that k just being a constant, what you can do is you can move the k out, do your integral, do whatever you got to do in there, and then you multiply the k back in at the end. We've already been doing that, so I don't know that that's brand new. We did that with indefinite integrals. You can also do it with definite integrals. So our example there, do you guys see the k in our example? What is it? 7. Yep, so the 7 could be pulled out. 7 times the integral from -5 to 8 of f of x dx. We have no idea what f of x is, so we can't really go from there, but that would be an illustration of this property. And then lastly, this one is old as well, but this one is potentially extremely useful. I will use this a lot. Notice it says the integral from a to b of a sum or difference. What you can do is you can rewrite this as the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. In other words, the integral of a sum is equal to the sum of the integrals. We've done this before. Doing it again here with definite integrals. It does not change anything, but I would say if anything, this is potentially more useful than, or this will be more useful in the future as compared to what we've done with it in the past. So our example here, you guys see it's a sum, so I could rewrite this to be the integral from 3 to 4 of x to the 5th dx plus the integral from 3 to 4 of 5 sine of x dx. And why I say this is so potentially hugely helpful, do you guys see how even based on what I've written, isn't there one more property that I could use to simplify it a little bit more? What could I do? Get the 5 out, right? The 5 is that constant multiple. So if I wanted to, I could say, you know what, that k actually can come out here. But if I didn't write those separately, it's potentially there. The potential issue is I might accidentally apply the 5 to both terms instead of just the second term. So by splitting it up, I think that it's quite useful. We have time for one of these here, so why don't you guys try number 9 real quick. For the following examples, these are going to be our rules right here. And we're supposed to evaluate the integral from -2 to 9 of 2f of x plus the integral from 7 to 3 of g of x dx. So take just a little bit here and see if you can come up with an answer. I'll show you the answer in a second. We'll use the other one as maybe a warm-up for next time when I see you tomorrow. Should be -10. 3 to 7 you get 10, but that's 7 to 3. It's easy to do. Guys, when I see you tomorrow, please, you will definitely want to watch the 4.4 video. It's called the Fundamental Theorem of Calculus. It's really important. When you come to class tomorrow, we will practice lots with that. You guys have a great day. See ya.